Welcome to DAR Tutors for online and home tuition. In this video, we will explore a critical topic in IB applications and interpretation higher-level mathematics, confidence intervals for a population mean with unknown variance. By the end of this session, you will be able to understand and apply the t-distribution, construct and interpret confidence intervals for a population mean with unknown variance, and solve IB-style problems involving the t-distribution and confidence intervals. This situation is very common in real-world applications, as we rarely know the exact standard deviation of an entire population. We will learn how to handle this uncertainty using a powerful statistical tool. Let's begin by recalling the familiar formula for the z-statistic, which we use to construct confidence intervals when the population standard deviation, sigma, is known. The formula is z equals the sample mean, x bar sub n, minus the population mean, mu, divided by the population standard deviation, sigma, all divided by the square root of the sample size, n. As mentioned, in most practical scenarios, we do not know the population standard deviation, so we cannot use this z-statistic. To overcome this, we must estimate the population variance, sigma squared. We do this by using the sample variance, which we denote as s squared. The formula for the sample variance is s squared equals the sum from I equals 1 to n of the quantity x sub I minus x bar, all squared divided by n minus 1. This value, s squared, is an observed value calculated from a specific sample. The quantity it estimates, which can vary from sample to sample, is the sample variance random variable denoted s squared sub n minus 1. A key property of this sample variance, s squared sub n minus 1, is that it is an unbiased estimator for the population variance, sigma squared. This means that if we were to take many samples, the average of their sample variances would equal the true population variance. This is why we divide by n minus 1 instead of n, a concept known as Bessel's correction. Now, what happens if we substitute this random variable s for the unknown population standard deviation sigma in our z-statistic? We obtain a new statistic, which we call t. The formula is t equals the sample mean minus the population mean, divided by the sample standard deviation s, which itself is divided by the square root of n. It's important to understand why this is a new statistic. When sigma was known, the denominator of our z-statistic was a fixed number. Now, the denominator, s over root n, is a random variable because it's calculated from the random sample. This added randomness means that t does not follow a standard normal distribution. So, we cannot use the standard normal tables or the standard normal distribution to calculate probabilities for t. It has its own unique distribution. This new distribution is called the t-distribution, or sometimes students' t-distribution. The t-distribution has a shape similar to the normal distribution. It is symmetric and bell-shaped. However, it is slightly flatter and has heavier or wider tails. This reflects the extra uncertainty we have from estimating the population standard deviation from a sample. Higher tails mean there is a greater probability of observing a t-value far from zero compared to a standard normal distribution. The shape of the t-distribution is determined by a single parameter called the degrees of freedom, which we denote as df. In the context of the statistic t we just discussed, the degrees of freedom are n minus 1, where n is the sample size. You can think of degrees of freedom as the number of independent pieces of information available to estimate a parameter. When we calculate the sample variance, we first have to estimate the sample mean, which uses up 1 degree of freedom. This leaves us with n minus 1 independent values to calculate the variance. So as a rule, when we use the sample standard deviation s to estimate the population standard deviation sigma, we use the t-distribution with n1 degrees of freedom. This is a fundamental rule to remember in this topic. A key property is that as the sample size n, and therefore the degrees of freedom de increases, the shape of the t-distribution becomes more and more like the standard normal distribution. For very large sample sizes, typically n greater than 30 or 40, the t-distribution is almost indistinguishable from the standard normal distribution. Now that we understand the t-distribution, we can construct a confidence interval for the population mean mu. The process is very similar to constructing a z-interval. We want to find an interval that contains the true population mean mu with a certain level of confidence, say 1 minus alpha. This means we are looking for values a such that the probability of our statistic t falling between negative a and positive a is 1 minus alpha. Formally, we write this as p of the quantity negative a is less than or equal to t, which is less than or equal to a equals 1 minus alpha. Because the t distribution is symmetric about 0, we can find these critical values a. Each tail will contain a probability of alpha divided by 2. We denote this specific value a as t sub n minus 1, comma, alpha over 2. Here, n minus 1 is the degrees of freedom, and alpha over 2 is the area in the upper tail. This is our critical t value. So, the confidence interval for the population mean mu is given by x bar minus the critical t value times the standard error s over root n, is less than or equal to mu, which is less than or equal to x bar plus the critical t value times the standard error s over root n. The first part, x bar, is our point estimate for mu. The second part, plus or minus the critical t value times the standard error, is the margin of error. The standard error, s over root n, is an estimate of the standard deviation of the sampling distribution of the sample means. Let's work through an example to see how to apply this formula. We'll use the data from example 7 in the textbook. A bakery wants to determine the average sugar content of their bread. They randomly select 30 loaves and measure their sugar content. We are given the sample statistics. The sample size is n equals 30. The sample mean, x bar, is approximately 15.897 grams, and the sample standard deviation, S, is approximately 1.365 grams. We need to construct a 98% confidence interval for the true average sugar content. Because the sample size n is 30, which is large, by the central limit theorem, the distribution of the sample means is approximately normal. We are told sigma is unknown, and we have the sample standard deviation S. This is the classic scenario for a t interval. First, we find our degrees of freedom. The degrees of freedom, df, is n minus 1, which is 30 minus 1, giving us 29 degrees of freedom. Next, we find the critical t value. Our confidence level is 98%, so 1 minus alpha is 0.98. This means alpha is 0.92. We need to find the critical value that cuts off alpha over 2, or 0.01, in the upper tail. So we are looking for t sub 29, 0.01. To find this value, we use a graphics calculator, for example the TI-84. We use the INVT function. On the TI-84, you go to second, then vars for dist, and scroll down to 4 for INVT. The INVT function requires the area to the left of the critical value. Since the area to the right is 0.221, the area to the left is 1 minus 0.1, which is 0.99. The degrees of freedom is 29. So we enter NVT of 0.9929. The calculator gives us a critical t value of approximately 2.462. This value tells us that for a t distribution with 29 degrees of freedom, 99% of the distribution lies to the left of 2.462. Now we have all the pieces to build our interval. Plugging our values into the formula, we get 15.897 minus 2.462 times the quantity 1.365 divided by the square root of 30. And the upper bound is the same expression with a plus sign. Calculating the margin of error, we get approximately 0.6136. Adding and subtracting this from the sample mean gives us our interval. The resulting 98% confidence interval for the mean sugar content is 15.28 grams to 16.51 grams. This means we are 98% confident that the true average sugar content of all bread loaves baked at this bakery lies within this range. Let's work through another problem. This time, we'll start with raw data. A sample of 30 torch globes was selected, and their lifetime in hours was measured. We need to construct a 95% confidence interval for the mean lifetime of all such globes. This is exercise 29F, question 4A and B. The first step is to enter the raw data into our graphics calculator to find the sample mean and sample standard deviation. Be careful to use the correct function, which is often one variable statistics or one var stats on a TI calculator. On a TI-84, you would press Stat, select Edit, and enter the 30 lifetime values into a list, say L1. Then you would press Stat again, Select KL key and choose option 1 of var stats. The calculator will then display the sample statistics. After the calculation, you should find that the sample mean, X bar, is approximately 82.027 hours, and the sample standard deviation, S, is approximately 3.9111 hours. Now we can proceed with constructing the confidence interval. Our sample size n is 30. The degrees of freedom are n-1, which is 29. The confidence level is 95%, meaning alpha is 0.05, and alpha over 2 is 0.025. We need to find the critical t-value, t sub 29, 0.025. Using our calculator's NVT function, we input NVT of 0.975, which is 1 minus 0.025, and 29 degrees of freedom. This gives us a critical t-value of approximately 2.045. Now we can build the interval. We plug our values into the formula. This gives us 2.027 plus or minus 2.045 times the quantity 3.911 divided by the square root of 30. Calculating the margin of error gives approximately 1.46. So our interval is 82.027 plus or minus 1.46. This gives a 90% confidence interval for the mean lifetime of torch globes of 80.57 hours to 83.49 hours. This means we are 95% confident that the true average lifetime of all torch globes is somewhere between 80.57 and 83.49 hours. A common type of problem in IB is to compare a confidence interval with a stated claim. Let's look at exercise 29F question 6. Fab Tread manufactures motorcycle tires. Their regular tread gives a stopping time of 3.45 seconds at 60 km/h. They claim a new tread reduces this time to 3.1 seconds. To test this claim, a sample of 36 stopping time measurements is taken with the new tire tread. This sample data yields a sample mean stopping time of X bar equals 3.16 seconds, and a sample standard deviation of S equals 0.14 seconds. We need to construct a 95% confidence interval for the mean stopping time and use it to evaluate the company's claim. Let's first build the 95 for confidence interval. The sample size n is 36, so our degrees of freedom are 35. The confidence level is 95%, so alpha is 0.05, and alpha over 2 is 0.02. We find the critical t-value t sub 35, 0.025 using our calculator, which is approximately 2.030. Now we construct the interval. 3.16 plus or minus 2.03d times 0.14 divided by the square root of 36. This gives a margin of error of approximately 0.047. The 95% confidence interval is therefore from 3.143 seconds to 3.207 seconds. Now for the interpretation. The company's claim was that the new tread reduces the average stopping time to 3.1 seconds. We can see that the claimed value of 3.1 seconds lies just outside the lower bound of our 95% confidence interval, which starts at 3.113 seconds. Because the claimed value is not within the interval, we do not have enough evidence to support the claim that the true mean stopping time is 3.1 seconds. Furthermore, the entire interval is above 3.1 seconds. This suggests that the true mean stopping time for the new tread is actually higher than 3.1 seconds, which directly contradicts the company's claim. Therefore, the production team's claim does not appear to be justified by the data. A very important application of confidence intervals is in hypothesis testing. We can use a confidence interval to determine if a population parameter has changed or if a sample comes from a specific population. Let's consider exercise 29F, question 8. Free-range chickens have a mean meat protein content of 24.9 units per kg. A battery cage study is initiated where 50 chickens are fed a special meal. The mean protein content of this sample is 26.1 units per kg, with a standard deviation of 6.38. The goal is to determine if this new feeding program for battery cage chickens increases their protein content to be higher than that of free-range chickens. We will use a 95% confidence interval for the mean protein content of the battery cage chickens. The parameters are: sample size n is 50, so degrees of freedom are 49. The sample mean X bar is 26.1, and the sample standard deviation S is 6.38. For a 95% interval, alpha over 2 is 0.5. The critical t-value t sub 49, 0.25 is approximately 2,000. We calculate the interval, 26.1 plus or minus 2,000 times 6.38 divided by the square root of 50. The margin of error is approximately 1.805. This gives a 95% confidence interval of 24.295 to 27.9. Now we compare this to the free-range chicken mean of 24.9. The mean for free-range chickens, 24.9, falls inside our 95% confidence interval for the battery cage chickens. Because the free-range mean is a plausible value for the true mean of the battery cage chickens, we do not have sufficient evidence at the 5% significance level to claim that the new feeding program results in higher protein content. The data does not strongly support this conclusion. This example beautifully illustrates how confidence intervals can be used to perform a hypothesis test, simply by checking if a hypothesized value lies within the interval. For expert tuition in IB A-Level and IGCSE curricula, please contact DART Tutors. You can visit our website at darttutors.co.uk. Finally, let's explore Exercise 29F Question 9, which requires us to work with the sum of squared deviations. We are told that a random variable x has a normal distribution with mean mu. A random sample of size 15 is taken, and it is found that the sum of squared deviations from the sample mean is 230. The formula for sample variance is s squared equals the sum of squared deviations divided by n minus 1. We have the sum of squared deviations, which is 230, and n is 15. So s squared is 230 divided by 14, which equals 164286. Part A asks for the sample variance. That is s squared, which is 16.4286. Part B asks for a k% confidence interval. Let's find the 95% confidence interval. We need the sample standard deviation, s, which is the square root of s squared. The square root of 16.4286 is approximately 4.0532. The degrees of freedom are n minus 1, which is 14. For a 95% confidence level, alpha over 2 is 0.025. The critical t-value t sub 14, 0.025 is approximately 2.14. We are not given the sample mean x bar. Looking at the provided solution, it states the 95% confidence interval is 124.94, 129.05. We can use this information to find x bar and k. The sample mean x bar must be the center of the interval, so we can find it by taking the average of the upper and lower bounds. X bar equals 124.94 plus 129.05, divided by 2, which is approximately 126.995. The margin of error for this interval is the distance from the center to one of the bounds. Margin of error equals 129.05 minus 126.9, which is 2.05. We can now check if our calculated margin of error matches the one from the provided 95% interval using our critical t-value of 2.4. Our calculated margin of error is 2.145 times 4.0532 divided by the square root of 15, which is approximately 2.25. Notice our calculated margin of error is 2.25, while the one derived from the interval, 124.94, 129.05, is 2.055. This discrepancy likely comes from rounding. For IB exams, it's best to keep more decimal places during intermediate steps. However, for a quick check, they are close enough. To find the value of k, we can use the margin of error of 2.05 from the provided interval. We set our margin of error formula equal to 2.055. Solving for the critical t-value, we get t sub 14, alpha over 2 equals 2.055 times root 15, divided by 4.0532, which is approximately 1964. Now we need to find what tail probability alpha over 2 corresponds to this critical t-value. We use the TCDF function on the calculator, or use an inverse t-table. On a TI-84, you would use TCDF from the critical value to positive infinity. This gives us the area in the upper tail. TCDF from 1.964 to 9099 with 14 degrees of freedom is approximately 0.0345. So alpha over 2 is 0.0345, which means alpha is 0.069. The confidence level is 1 minus alpha, which is 0.931 or 93.1%. Therefore, K is approximately 93.1. This problem demonstrates how to work backward from an interval and use all the pieces of the formula. We have now covered the theory and application of confidence intervals when the population variance is unknown. We introduced the t-distribution, learned how to find critical t-values, and used these to construct and interpret confidence intervals. You are now able to tackle problems where the population standard deviation is unknown, which is a key skill for HL-level statistics. For practice and to solidify your understanding, we will now provide at least 5 IB-style practice questions based on the concepts we've learned. You should attempt them on your own before watching the fully worked solutions that follow. Here is your first practice question. A random sample of 25 workers from a factory recorded their commute time to work in minutes. The sample mean was 35.8 minutes, and the sample standard deviation was 6.2 minutes. Assuming commute times are normally distributed, construct a 90% confidence interval for the true mean commute time for all workers in the factory. Pause the video here and try to solve this question. When you're ready, we'll go through the solution. Let's review the solution for practice question 1. First, let's identify the key information. We have a sample size n of 25, a sample mean x-bar of 35.8, and a sample standard deviation s of 6.2. We need a 90% confidence interval. Since the population standard deviation is unknown and we are given the sample standard deviation, we use a t-distribution. The degrees of freedom are n-1, which is 25 minus 1, so 24. For a 90% confidence interval, alpha is 0.10, so alpha over 2 is 0.05. Using our calculator's NVT function for an area of 0.95 and 24 degrees of freedom, we find the critical t-value to be approximately 0.711. Now we can construct the interval using the formula. The interval is 35.8 plus or minus 1.711 times the quantity 6.2 divided by the square root of 25. This simplifies to 35.8 plus or minus 2.12. This gives us a 90% confidence interval for the mean commute time of 33.68 minutes to 37.92 minutes. This means we are 90% confident that the true average commute time for all workers is between 33.68 and 37.92 minutes. Here is practice question 2. A study investigates the effectiveness of a new fertilizer on plant growth. A random sample of 18 plants treated with the fertilizer shows a mean growth of 4.5 centimeters with a standard deviation of 1.2 centimeters. Part A asks you to calculate a 95% confidence interval for the true mean growth of all plants treated with this fertilizer. Part B asks you to interpret the confidence interval you calculated. Take a moment to work through this problem. Let's review the solution for practice question 2. We have n equals 18, x bar equals 4.5, and s equals 1.2. We need a 95% confidence interval. The degrees of freedom are 17, and for a 95% interval, alpha over 2 is 0.025. The critical t-value t sub 17, 0.025 is approximately 2.110. Plugging into the formula, we get 4.5 plus or minus 2.1 times 1.2 over root 18, which is approximately 4.5 plus or minus 0.597. This results in a 95% confidence interval of 3.9 centimeters to 5.1 centimeters for the true mean growth. For part B, to interpret the interval, we would say, we are 95% confident that the true average growth of all plants treated with this new fertilizer is between 3.90 centimeters and 5.1 centimeters. Here is practice question 3. A food manufacturer claims that a new snack bar has a mean carbohydrate content of 20 grams. A random sample of 15 snack bars is tested, and the mean carbohydrate content is found to be 21.3 grams with a standard deviation of 2.1 grams. Part A. Construct a 98% confidence interval for the true mean carbohydrate content of the snack bars. Part B. Based on your interval, do you have sufficient evidence to doubt the manufacturer's claim? Pause the video and attempt this problem. Let's review the solution for practice question 3. The parameters are n equals 15, x bar equals 21.3, s equals 2.1. We need a 98% confidence interval. Degrees of freedom are 14. For 98% confidence, alpha over 2 is 0.01. The critical t-value t sub 14, 0.01 is approximately 2.624. The interval calculation gives 21.3 plus or minus 2.624 times 2.1 over root 15, which is 21.3 plus or minus 1.42. The 98% confidence interval for the mean carbohydrate content is 19.88, 22.72. Now for part B. The manufacturer claims a mean content of 20 grams. The claimed value of 20 grams falls within our 98% confidence interval. Since it is a plausible value for the true mean, we do not have sufficient evidence at the 2% significance level to doubt the manufacturer's claim. We can't say it's wrong, but we also can't say it's definitely right. We just don't have enough information to refute it. Practice question 4. The width of a 95% confidence interval for a population mean is given by W equals 2 times the critical t-value t sub n minus 1, 0.025, times the sample standard deviation s divided by the square root of n. A researcher constructs a 95% confidence interval using a sample of 25. What sample size would be required to reduce the width of the confidence interval by half, assuming the same confidence level and standard deviation? Give your answer to the nearest integer. Solve this problem and then check your solution. Here's the solution for practice question 4, which deals with the width of a confidence interval. The formula for the width W is W equals 2 times T times S over root N. We are asked to find a new sample size, N prime, such that the new width, W prime, is half of the original width W. So we set the equation 2 times T prime times S over root N prime equal to half of our original width expression. Several terms cancel out. The 2 on the left and the 1/2 times 2 on the right, and the standard deviations on both sides. This leaves us with T prime over root N prime equals T over root N. Since the sample sizes are not the same, the degrees of freedom are different, which means the critical t-values will also be different. We must include them in our calculation. Let's find the original critical t-value. For n equals 25 and 95% confidence, df is 24 and t is approximately 2.064. Substituting our known values, we have t prime over root n prime equals 2.064 divided by 5. We have two unknowns, t prime and n prime. A common simplification in IB problems, especially when the sample sizes are expected to be large, is to assume the critical t-value doesn't change significantly and instead use the z-value of 1.96. Another approach is an iterative process. For now, let's assume the t-value changes, as that is more accurate. Let's test an n prime that would give a much smaller standard error. Let's try n prime equals 96. This is double the sample size of T4. For this, df prime is 95, and t prime is approximately 1.985. Now we check our equation. Is 1.985 divided by the square root of 96 equal to 2.064 divided by 5? We find that 0.202 is approximately 0.413. This doesn't work, so we need a different approach. Let's restart with a more direct method. We want W equals W2. This means our new margin of error is half the old margin of error. Margin of error equals T times S over root N. We want the new margin of error to be half of this. Simplifying again, we get T prime over root. N prime equals T over 2 times root N. We can start by ignoring the T values and solving for the required increase in N, then check if the T values justify our N. To halve the width, the standard error must be halved, which means the denominator, root N, must be doubled. For root N to be doubled, N must be quadrupled. So, 4 times 25 is 100. Let's test N prime equals 100. For N prime equals 100, The degrees of freedom are 99, and the critical t-value t sub 99, 0.025 is approximately 1984. Let's substitute our values into the width equation. The original width is approximately 10.32. The new width is 10.32 divided by 2, which is 5.16. Now we check if the new width is approximately half the original width. We calculate the ratio W prime over W. 0.39688 divided by 0.8256 is approximately 0.48. This is very close to 0.5. So, a sample size of 100 is indeed the correct answer when rounded to the nearest integer. So, the required sample size to have the width of the confidence interval is t prime equals 100. Here's our fifth and final practice question. A random sample of 100 students is selected, and their average score on a test is 75 points with a standard deviation of 8 points. Suppose the true mean score for all students is mu. Part A. Construct a 99% confidence interval for mu. Part B. An educator claims that 99% of all possible samples of size 100 will produce confidence intervals that contain the true mean mu. Is this claim accurate? Explain your answer. This is a very important conceptual question. Give it a try. Let's review the solution to practice question 5. For part A, we construct the 99% confidence interval. We have n equals 100, x bar equals 5, and s equals 8. The degrees of freedom are 99. For a 99% interval, alpha is 0.01, so alpha over 2 is 0.05. The critical t-value t sub 99, 0.05 is approximately 2.626. The interval is 75 plus or minus 2.626 times 8 over root 100, which is 75 plus or minus 2.10. The 99% confidence interval is 72.90, 77.10. Now for part B, the conceptual question. Is the educator's claim accurate? The answer is no. The claim is inaccurate. The correct interpretation is that if we repeated the sampling process many times, 99% of the confidence intervals we construct would contain the true mean mu. A single specific interval either does or does not contain the true mean mu. We don't know which one it is for our particular interval, so it's incorrect to say that there is a 99% chance that our interval 72.90, 77.10 contains the true mean. The 99% confidence refers to the reliability of the procedure, not the probability that our single interval is correct. This distinction between the process and the result is a crucial conceptual point that IB often tests. Always remember that confidence is in the method, not the outcome of a single sample. We have reached the end of our session. We have thoroughly covered confidence intervals for a population mean with unknown variance, a key topic for your IB AI-HL examinations. You should now be able to identify situations where the t-distribution is appropriate, calculate and use degrees of freedom, find critical t-values, and construct and interpret confidence intervals. Furthermore, you can now apply these skills to solve complex IB-style problems, including those that involve comparing intervals to claims and understanding the fundamental meaning of confidence. This is a powerful set of statistical tools that you will find useful not only in your studies, but also in real-world data analysis. Thank you for watching. For personalized expert tuition in IB A-Level or IGCSE curricula, please don't hesitate to contact DART Tutors. You can visit our website at darttutors.co.uk to find out more. We look forward to helping you achieve your academic goals.